So if you look at the code, actually, the demo code, basically the function calls the demo code calls a binary MRF function, which basically tries to find the maximum assignment of something of the form sum over i's of j's of w by j xi xj, something of that form. Where I think I told you what these w's should be in the question. And these b's, I don't say actually in the question what they should be, but you should just take them as the same setting as they were in the demo code. And the reason that they are set in the way that they are is that, remember that what we want to do is we want to encourage pixels to be in the same neighboring state, which is given by this term here. We want them also to be encouraged to be in the same state as the actual observed pixels as well. Well, these observed pixels, though, they're the noisy quantities. So let's call, if xi tilde is the observed noisy pixel, what we would like is that we want this term here to bias us towards that noisy pixel state. So we would like, ideally we would like the solution x to be in the same state as b, provided that it's in agreement with its neighbors. Okay, so what we could do is, well, if we take 2 times xi minus 1, if xi is 0, 1, and xi is 0, 1. So this is the noisy one. This is the clean one that we're trying to reconstruct. If I take this would be the plus or minus 1. This will either be plus or minus 1. So if this is 1, this remains a 1. If this is 0, it goes to minus 1. So clearly what's going to happen then is that if they are both in state 1, this whole thing will have value 1. If they're both in state 0, that goes to minus 1 times by minus 1, which is 1 again. So if they're in the same state, this contributes a value of plus 1. If this is say state 0, I get minus 1. If this is state 1, I get plus 1. So I get a minus 1 contribution. Similarly for the case. Okay. So what this transformation is doing is it's favoring, you get a plus 1 contribution when x is in the same state as the noise pixel. So just expanding this out, so these x tildes are given, they're fixed. Okay, so this is equal to 2 xi tilde 4 xi tilde. Plus some constant. So what I'm trying to say is that I only care, I'm going to be maximizing this function with respect to x. So anything else is a constant. I don't care about added constant. So the x dependency here is 2 xi times by 2 xi tilde minus 1. Right, so I forgot what I did in the code exactly, but I probably said something like, so my bias variable here in my code, b should take the role, if I've done this right, I don't know if I've done it correctly actually. That would have been the matching of this term to this term here. And I don't remember what was going on in my code, right? But that was the, that should have been what I should have done anyway. Now, and obviously, if there's a feed factor here, I might have not put the 2 there, I might have put 1 there. I can't remember what I did, but whatever it is, it's just, it's just describing the strength that you would like then this term to, that the noise would actually be in agreement with the clean image. it doesn't really matter. So, but the point is that, you know, please just stick with whatever I did in the code. You should already, you know, just do that. If for some reason you're missing a factor of, you know, you put 1 or 2 here, I don't really mind that much. It's not a big deal. The important thing is to try to understand how the algorithm works. Is, you know, do the iterative algorithms for cleaning up the thing. That's the main one. I don't know if any of you tried to use the original code for this. Did you try to do that? For those of you. Yeah, I wouldn't recommend it. Well, it's certainly not on my laptop anyway. So. I was doing it a little bit sneaky. I mean, you can look at the code for inspiration, but at least the way MATLAB works is it's actually not a good way to program it for MATLAB reasons. It would work okay in some other language, but MATLAB is, you know, the way it's particularly coded there is not ideal. So in the next version of the software, I'll just rechange that so something that works rather better. And I believe there was a typo in the assignment. I said somewhere you have to minimize this function. Of course, I mean maximizing it. But those of you who already spotted that one, very well done. I think that's it. Any more questions about the assignment? Apart from it is tomorrow. Some point. Okay.
Just to check again, it's tomorrow at noon.
It's tomorrow at noon. Yeah.
I'm really hoping I could be at night.
Well, that's good because it gives you more afternoon. You're free to do other stuff. All right. So, how did you find it? I mean, is it going okay? It shouldn't be. I mean, there's 3 of you per thing, right? So it's kind of you share the load, I guess. Is it going okay, or I don't hear any major complaints so far? So I assume it's going okay.
When are you next planning on setting the next?
Soon.
Oh, okay.
Next week.
Ah.
How many assignments will there be overall?
There'll be 3 to 4. I mean, the other thing to say, you know, by the way, is that I view assignments mainly as instructive things, so to try to help you understand the material. There are some more difficult questions in there as well, to challenge people as well. But you know, the way the marketing scheme is designed such that I want you to, you know, you're not going to get penalized by not doing a very hard question or something like that. I don't really care. It's just to sort of see if there's some stellar people in the audience, you know, that maybe to get the last few percent, you know, you have to do a lot of work. But the next assignments actually will be a little bit more interesting.
That's a good thing.
Are they all the same format? Are they all questions from the book, or have you got something? Okay.
No. Most of them will be, but there will be some Okay, so somebody asked me, now, what the heck is all this junction tree thing for? You know, what's the point of it? So the point is that, okay, if you have a singly connected structure, you can use the junction tree, the factor algorithm, or whatever other formulation you like, right? Just some message passing thing on a singly connected structure directly. In other words, there exists, you know, for the belief network or the market network, there exists actually even, you know, before people thought about using this factor graph representation, we didn't use them. We just used the direct belief network or the direct market network, and we just ran belief propagation on those graphs directly. We never compiled even the belief network or the market network into another structure. We just did the message passing on the original graph structures, which is fine. It always works. I mean, this factor graph formalism is just a recent sort of thing, which is not really necessary. The point, though, is that you cannot get the correct answer when the graph is multiply connected by doing that. You cannot any more work with the original graphical representation, either belief or Markov network, or factor graph transformation, and do some form of inference by message passing on that graph to get the correct answer. Formally speaking, it will not work. That's why in the multiple connected case, we need another representation for which, when we do message passing on that representation, it will work. Okay, that's the reason for this painful stuff that we're going through now. It's not necessary for the things that you've seen so far because they were singly connected. So you could have run your favorite belief propagation algorithm already to do this, but you will not be able to do it in a multi-connected case. So what I'm going to show you now is how to compile a multi-connected graph into a corresponding clique or junction tree, for which then the message passing will work. Okay. So let's take this Markov network. What is the factor graph for this guy? It's A, B, C, D. So it's a loopy, non-singly connected, multiply connected factor graph. So there's no edge where we can begin the belief propagation algorithm. It doesn't work. You could attempt to initialize things at random, carry out the updates of the message passing, cross your fingers, and hope you will just get the correct answer. Sometimes it will, sometimes it won't. Okay, in general. So we're stuck. Okay, so the question is, can we though use another representation? Well, let's try to do the same things we've been doing all this whole talk today, which is to represent this graph in terms of its marginals. Okay, so original margin inference, that's what we need to do. So let's figure out what is P of ABC. It's given by the sum over D of the joint. So that means we can write just so in other words, P okay, so so I claim this is true. So why is that true? Well, it's clearly true.
Why it's true.
If you take,
Can I use that in my exams?
this expression here, and plug it into here, what do you get? You get this term here, and this term here, multiplied by this term here and this term here, which is P. And you get this term here divided by that term there. So it's true. Okay. So by symmetry, this expression is true. Well, that's clearly true anyway, it's just a marginal term. So that means that we can write ABCD to be equal to so this term here basically is that there, so we can use that to be the marginal here divided by this sum. Okay. So then we're going to get the product of the two divided by this sum and this sum. Again, this good thing about this is it's just P again, it's summed over these two variables, so it's just a marginal. Okay, so that's kind of interesting. So what does it mean? It means that I've been able to represent the multiplicated graph. So this one, this Markov network here, actually it's a clique graph. We realized we could represent this as P of A, B, C, P of B, C, D, over P of, what was it?
AC.
BC. Is that right?
No, it's the common pair
So,
between them.
yeah, ABC. Okay, so that's interesting. Right? I mean, this is our usual trick. But what's important about this is that we don't have now two cliques only. We have three cliques over here. Okay. So another way to think about these operations I was doing here is that I summed over D. So I'm kind of passing information, if you like, to the rest of the network. Right? So what's going to happen is that when I sum over D, well, I'm going to get my original cliques are A, B, B, C. We're going to get another clique there, which is a function of C and A. Okay? So that means we're going to have an A, B, B, C, and a C, A function there in the marginal. Okay? So we're going to effectively, when we sum over D, we're going to be getting a sort of a new marginal, which is a function of the clique itself. So what I'm effectively doing in those operations is I'm saying, well, given this marginal, can I re-represent the original graph? And I realize that the original graph actually, in some sense, then is equivalent to this representation here. So let's explain this. Yeah. Okay. So. So one way to think about this is that if you didn't know anything about, say, junction trees, and you tried to just do inference with the original Markov network by eliminating variables. Let's look at this one here. Here's a Markov network, okay, and you want to figure out, say, what is the marginal for, say, P to C. So let's imagine that the normalization constant is correctly absorbed into one of these potentials. So all we have to do is to sum over A, B, D, E, and F with the variables. So how do you sum over the variables A, B, D, E, and F of this whole? Well, if you started by summing over F, right? You're going to then have a new term which is going to couple together whatever F is connected to. So because we're going to have a term, down here, we'll have a term phi of A and F, and a term phi of E and F. And when we push this sum over F into here, we'll get a function here of the neighbors of F, whatever that is. So it's effectively, when I've done that summation, I'll end up with a graph, a new graph, which has got that form here. Like, imagine that this F is not there. We'll have that link with it. Okay. And then I could continue and say, well, now maybe I'll sum over A, for example. And so I'll introduce a link to whatever A is neighboring to in the reduced graph. But A is already connected to, there's already a link between B and E, so that's not going to add anything. So effectively, if I were to sum over F, I'll get a new graph with this link in here, F would be removed. And then sum over A, I get a link here, A will be removed. And I could continue, I could then sum over E, and this would add a link between B and D, and then I could sum over, say, B, which has this link here, which is already there, is somewhere in D. Okay, so this is interesting because what it means is that whilst this graph is loopy, it's multiply connected, actually there exists a sequence of operations which clearly, if this were to extend much further, and so that you had many sort of ladders, if you like, on this rungs on this long ladder, it's clear that the computational cost of carrying out this marginalization operation for a node at the end of the ladder is still linear in the number of variables, even though it's multiply connected. Right? Because all I'm doing is I'm just changing the local graph structure. I'm triangulating it. Right? I'm adding these links between neighbors of nodes which are eliminated at each stage. Right? And as long as this fill-in structure, this triangulation mechanism is not going to increase fundamentally the complexity of the linkage structure in the graph, I'm going to be okay. I can continue to identify edge nodes in the graph which I can eliminate sequentially. Okay. So what's going to happen is that you could think about doing that and then add in all of the variables that we, adding all the edges, the links in this graph for variables that were eliminated in this process. And what that would mean is that I could then go back and I could go back to the start and say, well, actually, if I'd had a Markov network of this structure, I could have also carried out the same. I could add, well, this link here, this, phi, the clique on this variable here, I just define it as before, and I just make a sort of a unitary, AE sort of function. It won't change it. It's the same thing. I could have then, so in other words, I could have easily carry out marginalization on a graph of that structure here, which is also simply connected, but it's got this triangulation property in it, such that there exists a sequence of eliminations of variables which will not increase the connectivity of this graph. Okay, so this is kind of key, right? This is the kind of the idea, in some sense, how to deal. One way to deal with this multiple connectivity. So what I could do now is say, well, okay, I can take this guy. If that's true, then I can compile that guy now into a clique graph and see how that looks. Well, let's do that. Let's do this one here. Have these out. Well, I think there was a simpler example before. I think I'll do this one as well. So this is actually what happens for this. The simpler example here. We can eliminate D. If we sum over D, we will end up with this marginal graph. And then we can say, well, okay, we can eliminate individual variables, say A and C, if we want to compute, say, the marginal B. Which means that we could have started actually out, we could have done variable elimination on this graph as equally as easily. So in all graphs of this form, we could do that. So what I could do is say, well, actually, then I can take this graph and write down the clique structure for this graph now. So we're going to click on ADC and a click on ABC. And this, look at that, is singly connected. Okay. The clique graph of this is not singly connected. What is the clique graph of that? Well, it's A to B, BC, CD, and AD, with some corresponding separate B, C, D, and A. So that's not singly connected. It's not a clique tree. Okay. But this one is a clique tree. So at the expense of having 3 cliques here rather than 2 cliques, sorry, cliques with 3 variables rather than cliques with 2 variables, I've managed to obtain a singly connected clique graph. for which I could then do message passing on this guy, and I would end up with the right answer. So what's happening on the other case, this more complex one here, is the same thing. So I could write down, so I claim that my original graph can certainly be represented in this way. Right? And there exists this sort of, procedure of variable elimination.
So David,
Yeah.
in the previous one, what would be the potentials on the new graph? Just would they just be the products of the?
Yeah. Well, actually, we'll do the assignment later. Maybe
Okay,
I'll come
sorry.
back to that one sec. But let's just, for interest's sake, see what happens in this case here. Well, let's write down the clique structure for that. So we've got a clique now on AFE, ABE, BCD, and BED. Okay, so let's do that here. So we need to link these cliques, right? Wherever they share a common variable, we're gonna have to link them. So these guys, they share E together. E is also in B already here.
Between
A is in here. E is in
and
here. We've got B and
B.
B is in here. And B and D are in here. I think that's it. Sure. So, as before now, this is not singly connected, but we can identify variables which appear on loops always. So let's look at E, right? So E is here in this loop. E, E, E. So as before, I can now scratch one of these, whichever one I want, and I will do it in a way which will render the graph simpler. Okay, singly connected. So the procedure before was, in general, we would find the maximum weight spanning tree from this guy, and then use that one as our tree structure. Right? So I'm not going to be able to do that in my head maybe, but it's clear that this is going to be weight 2, weight 2, weight 2, weight 1. So we're going to try to get rid of the low weight connections. So let's get rid of this one here. And let's get rid of this one here. Okay, so I'm now left with a singly connected clique tree. Let's just verify it satisfies the running intersection property. So let's look at all the variables. A, okay. B is here and here, and it's here, so that's okay. C is just in that, okay. D is just here. E is here, and F is just there. Okay, so running intersection is good. So we've got a junction tree, right? So what this essentially means is that I can now run absorption on this graph, and I'll be okay. I'll be able to do marginal inference. And it's going to be, what is the complexity of doing that? Well, I'll have to pass a message from, absorb from this node through the separator to that one. In order to do that, I have to sum over states of variable f here. And that will be a message over the combined set of variables A and E. So let's say all these variables are binary, for sake of argument. Okay, so that would be a table containing 4 states. And in general, the complexity of representing these tables will be exponential in the number of variables within a clique. So ideally, what we'd like is that these potentials are as small as possible in terms of we don't want many variables in each of these cliques, because it's going to be exponentially heavy to represent these potentials. Okay, so the smallest cliques we can have, the better. But then it's fine, it's going to be linear in the number of cliques. So the complexity will be linear in the number of cliques, but it'll be exponentially dominated by the cost of passing messages between, for the largest size clique. So roughly speaking, it will be linear in the term of number of cliques times by the complexity of representing the largest clique. Something of that order. So what I'm trying to impress upon you is that there exists a transformation of a multiply connected graph, in this case here, to another multiply connected graph. Right? Which, that transformation is special in the sense that it always gives rise, it will always give rise to a clique tree, a clique graph, which can be transformed to a clique tree by the usual dropping of any repeated variables in a loop. Okay. And so I'm not proving any of this stuff. You can look in textbooks, not the mine, it's like that. But in some sense, this kind of stuff is, the more you think about it, the more obvious it becomes, really. Okay, so what about, let's just, I'll come back to the assignment question in a minute, but, so this, for reasonably obvious reasons, this process of this transformation of the multiplicative graph to another multiplicative graph for which this property is okay is called triangulation. And really, there are many different triangulation algorithms. This is a mathematical, this is the terminology mathematicians use. The physicists call it decimation. The computer scientists call this forming a caudal graph. Statisticians call this forming a junction tree. It's the same thing. Every community's got its own, because it's so fundamental in science, this mechanism, that every community has rediscovered it with their own terminology. So you may think this sounds all very esoteric, but it's fundamental in science. Okay. So there are many different algorithms which are going to make a triangulation. Okay. In other words, so triangulation, a triangulated graph, for my definition, is there exists a sequence of variables that you can eliminate, such that when you eliminate a variable, you add connections to the neighbors of that variable eliminated. And if the graph is triangulated, there exists a sequence such that you will never add any more links to that graph. Right? You get that idea? So this one here is triangulated because I could eliminate F, A, the sequence would be F, A, E, B, C, and D, for example. If I did that, eliminated that way, I would not add any more connections to this graph. Of course, if I said, well, let's eliminate E first. If I eliminate E, I have to add links to all neighbors of E. Well, let's do an easy one. Let's eliminate A first. If I eliminate A, I'll add a link between E and F. Okay. So that would not work. Right? So it's not that a triangulated graph, it doesn't mean that if I eliminate variables in any order, that I will never add a link on this graph. That's not what it means. It means that there exists at least one elimination scheme which does not add links to the graph. Okay, and there can be many other, I could have triangulated the graph differently. I could have said, well, you know, this one will also be, just trying this schematically, I could have, that one would also be absolutely fine. Or this one is also fine. There are many such triangulations, and each triangulation corresponds to an elimination sequence. So one way to find this graph, this triangulated graph, so there are many, is actually just to do it, just to start with some variable, eliminate it, add a link between the things, find another variable, eliminate it, add the links, filling in these links as you go along. Now so this is the procedure of doing this fill-in, this triangulation, and it will result in a triangulated graph. But it doesn't guarantee that I will end up with. So what I'm trying to do is try to find a graph which doesn't have very big cliques in it. So if I'd started out by eliminating, say, E, that would have been kind of a bad thing to do, because I've got to add links now to all neighbours of E when it's eliminated. And when I do that, if I can draw it right, I've got an A, B, C, D, E, and F. So I eliminate E, I have to add a link between all neighbours of E. So what are the neighbours of E? Well, these have already got this, so this gets a link. No, it doesn't. What is E connected to? So this one. Well, maybe it was not so bad.
And one directly between F and D? Or you just...
F and D, yeah. I mean, this is maybe not such a great example. Let's look at another. Let's imagine you had a variable in the middle of this kind of a bespoke situation like this. If you eliminated, say, this node here, it wouldn't be so bad, right? You just add a link here. And you could then eliminate it, this one, and add a link here, and a link here. And you end up with a polygon just of a reduced number of edges. Right? And you could repeat, so you could see that that will be easy. You'll end up with a, a kind of a not too bad situation. And then if you decided to eliminate this one, you've got to add that all of these variables are neighbors. And then the graph becomes completely fully connected. So there are poor choices of this elimination. So a very naive thing to do is say, well, which node should I eliminate first? Maybe I should choose a node which doesn't have very many neighbors. This is a bad one. It's got tons of neighbors, tons of edges coming out of it. So this maybe is not a good one to start with. So maybe I'll at each stage I'll identify the node or a node with the least number of neighbors, and I'll eliminate that one next. Okay, that's a schedule, which is a heuristic. But you can run with it, and it will give you a triangulated graph. And then you might ask, well, because we're trying to find the graph, the triangulated graph with the smallest clique size as possible, then you might say, does there exist an algorithm which guarantees us to find the triangulated graph with the smallest cliques? And the answer is that there doesn't exist one. Well, there's no efficient algorithm which will do that. So it's NP hard. So unfortunately, there's no way to generally do this. This triangulation step is necessarily a heuristic step, in the sense that there's no provably efficient algorithm to do this. But this kind of heuristic, saying eliminating nodes with the least number of neighbors, is what I personally do. I think it's not bad. Okay, so let's just we'll come back to the assignments eventually at some point. Let's just do a slightly more complex example. So you've got this markup network here. So again, this is horribly multiply connected. You could not run, factor graph algorithm here. It won't work. We're going to compile this into a representation which will work, or which is a junction tree algorithm. So where should we start? So we need to, it's not triangulated. I know it looks triangulated, but it's not triangulated. So I should say that another definition of triangulation is a graph is triangulated if for every loop of length 4 or more, there exists a corner shortcut. So this graph is not triangulated because there is a loop of length 4 with no shortcut. There's no chord. That's why the triangulated graphs are also called chordal graphs by mathematicians. Okay. So I claim that this graph here is not triangulated because it's not chordal. So let's see if we can see that. Does there exist a loop here of length 4 or more which does not have a shortcut? I can see one. I don't know if you can see one. I think this one here, so C, G, J, K, H, back to C. It's a loop of length 4 or more, which is 1, 2, 3, 4, 5 in this case. And there's no shortcut in this thing. So maybe another simpler picture would be, let's take our pentagram. Is this triangulated? No, right? Because there exists a chord, a loop of length 5 with no chord. So we could say, well, let's add a chord. This would be, the result effectively of eliminating this variable. Does this graph have a loop with length 4 or more, which doesn't have a chord? The answer is yes, it does. This is one here, so we could get rid of that by doing that. That would effectively correspond to eliminating that variable. Does this graph have a loop length 4 or more, which doesn't have a chord? No, it's not. This is triangulated. Equivalently, we could have eliminated this variable with this variable, and then we just back to triangle. So clearly, we can then do inference in linear time in this corresponding structure. So, what would the algorithm do here? You would say, well, where to start? Let's start from a variable. Let's eliminate a variable which has the least number of neighbors. So this is a good candidate here because this guy's only got 2 neighbors. All the others, apart from this one, have got 3. So we could start with here. Sorry, this was 2 neighbors. So if you eliminate this one here, I'm going to sort of shade it down and add links between the corresponding neighbors. But they've already got an edge here, so that's good. That's good. That's good. I'm down now to this black graph here. And I have to find a node with the least number of neighbors there. So they vary 1, 2, 3, 4. That's not good. 1, 2, 3, 4. That's not good. This one's good. It's only got 3. That's the best I can do. So let's so B is also good. Let's eliminate B. 3 first. So I had a link between the neighbors. So these guys have already got links. They're neighbors of B. But these don't have a link here. So unfortunately, this elimination will add a link to this graph. Okay, fill in there. Okay, that's a little bit bad because it means that now I have a 4-clique. But never mind. That's doing by symmetry, we do the same on the other side. Now back to this reduced graph, the black one. Okay, so now which one are we going to eliminate? Well, C is not good because that's got 4. So maybe one of the other ones is okay. So let's do eliminated F, I think. So I added a link now between this one on the right side, and then eliminated G up to H down to this. And now we compile everything back into fill back on all of these links, added Turing links. This is our triangulated graph. This graph is chordal. You'll find that this definition of chordal and triangulation is they're equivalent. So it's a kind of funny terminology. It looked like it's got triangles on it, right? But it's not triangulated. This is triangulated. So now we take the junction tree. So we take this graph, find all the cliques in this graph. So what have we got? We've got a 3-clique here, A, B, F. got a 4 clique here, B, C, G, F, etc. There is hopefully only 4 cliques there. We write down all these cliques. These are all the cliques here. Okay. Then we do the maximum weight spanning tree to identify a clique tree from this horribly messy structure. And then we just draw the graph. And here is a clique tree, a junction tree. And it satisfies the running intersection property, which we could laboriously verify. Maybe just a couple. Let's look at the variable c. Just check if that's okay. So c is here, 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 here. So that's good. Right? So I mean, to give you another idea, let's imagine why this running intersection property is required. Let's imagine that c appeared here. And in isolation it appeared over here as well. And there was nothing connecting these two. There was no path connecting these two C's. It means somehow there's no reason that the marginal for C over here would ever be in agreement with the marginal C over there, because they're not communicating with each other. There's nothing to force the agreement between them. Okay, so now we need to do the assignment. We need to assign the potentials on this junction tree to the ones in the original Markov net. So how do we do that? So we have to go back now all the way down to here. Right? So on this graph now, we've got clique potentials. Let's start with this one, but the clique ABF potential. And we need to drop that in to a clique on the junction tree. So ABF, where can that go? Well, that's clearly going to go in this one here. So we drop it in. And similarly for all of the other potentials on the original Markov graph. Okay. And just to make sure that we're okay, we'll set all these separator potentials initially just to 1. Okay, because then that means that, as before, the product of all these clique potentials divided by the product of all the separator potentials will represent the original Markov network. So that's good, right? I don't think it happened in this case, but just to point out that it could happen, it does happen, that you may find a clique here for which no potential gets assigned to it. Okay, what do? You just set it to 1. You don't set it to 0, because any assignment is okay as long as the product of the separators, so cliques divided by separators, equals your original distribution. Any way of doing it is fine. There may even exist wacky ways of assigning separators to non-unity and cancelling them out somewhere else in the clique potential. It's fine as well. It doesn't matter. So this is something to bear in mind. Often people get caught out by the fact that they don't realize that when this clique potential is empty, actually means you set it to 1. So that's it. So that's the junction tree algorithm. So it's a long story and maybe a little bit confusing. So let's step back a little bit. So the big picture is, the good news is that you now have an algorithm which you can use to perform marginal inference in any graph, any Markov or belief network, whether it's singly or multiply connected. So how does it work? First of all, if it's a belief network, you've got to moralize it. You've got to compile it first into a Markov graph. So we start out, if you started out with a belief network, you need to compile it to a Markov network. That's the first stage. This graphical compilation involves moralization, marrying parents of the graph, which are not married. The next step is triangulation. We need to take this Markov network and ensure that we make a new representation which is triangular. This is the clique graph. Right? And there are many algorithms for doing that. And I showed you one of them. This results now in a clique graph, not necessarily, unfortunately, it's not necessarily the one with the smallest clique size, but it's one. Okay. Then what we need to do is need to identify a clique tree or a junction tree, or whatever you want to call it, by doing this maximal weight spanning tree. In other words, we need to remove any things in the graph here which are not a tree. But we need to do that in the correct way. So we will end up with this clique tree representation, which is a junction tree. Then what we need to do is we drop in to here whatever the original potentials were, either from the belief network, we need to drop them in to the potentials on the junction tree, wherever they can fit. And or if we start from a market network, we do that. Doesn't matter. You either do it directly or from an Markov network. It's the same. Okay, and then you run absorption. On this thing. Okay, and then you're done, because the marginals of this. The cliques on this graph, after doing this massive passing, will contain the marginals of the original distribution. Okay? Or if you wanted to find the most likely state, we do massive passing again, but we just do replace this sum with the max operation. And we're done. So it seems a bit of a complicated process, but that's how it goes. So so this question we had last week, one of the exercises. So I'm not proving any of this. So there are ways of proving these things. But so we started off with this pentagram, right? And I called this very 1, 2, 3, 4, 5. So you could do this by hand, like I tried to do on Friday. But this clearly, I don't remember what the exact thing, but this would be one valid triangulation. Because of that, I know then that the corresponding clique tree will be 1, 2, 3, 2, 4, 5, and 2, 3, 4. These guys share 2, 3 in common.
1, 2, 5 is the first one.
Oh, sorry, 1, 2, 5. 2, 3. Sorry, just 2, isn't it?
Yes.
2, 4. And 2, 5. Is that right?
Yep.
Yeah, that's good. Okay, so I don't remember, what I said, but there are different triangulations. But we're in this situation now where I've got a 2, which is on this loop. So the maximum weight spanning tree would be this one. So that means I know then that there exists a clique representation, junction tree, of the form P of x1, x2, xy multiplied by P of 2, 4, 5 multiplied by x2, 3, 4 divided by the separators, which is going to be P of 2, 5 divided by x2, x4. So in other words, any distribution any distribution of 5 variables which has got which is in this Markov form can be represented in terms of its marginals in this way. That's absolutely guaranteed. I didn't prove it, but you get to begin to build up the intuition as to why this is true. So, the idea last week was to show you, more accurately that indeed it is true. You can derive that by hand. Okay, so this may all give some more intuition. This may all look very mysterious, but in some senses, it's also quite easy. Let's look at a simple case with a belief network. Let's start out with this one. Let B goes to B goes to C. Right, so we've got P of C given A, B, C. Is equal to P of C given B, P of B given A, and P of A. Right, that's the belief network. Now, could you choose Bayes' rule to say, well, P of C given B is equal to P of C and B divided by P of B. P of B and A is P of B of A, P of A, P of A. They cancel. Look. P of A and B, P of B and C, P of B. Great, right? So, the same thing, right? What is the Markov property? It's Markov network with this. Clique graph with this. So another way to think about this is, physicists might say that it kind of makes sense to them because this kind of got a concept of dimensional consistency, if you like, in the sense that let's just count the variables here. So A occurs once in the numerator, B occurs twice in the numerator. So that's not good. We better cancel that with one of these. And similarly for the other guys, here, 2 appears in the numerator 1, 2, 3 times. So you better cancel that twice. Yeah. And then so at least it kind of then makes dimensional sense. Okay, so let's look at a slightly more complex example. This one often comes up in exams, so I will wake you up in case you're struggling. Okay, so here we are. Here's a belief network on the left. We're going to look at this and say, crikey, that's horribly multiply connected. Of course, you could do, what we'd like to do is to, just have an algorithm which will do the inference for us to then compute, say, P of C. So we're going to make a Markov network. So we're going to do moralization. So let's see what that does. So they're the blue links, right? We're going to marry parents together. So they are the blue links here. Now imagine we've got the graph where we've got a new graph with the blue links in it. Okay? And you need then to take that Markov network, including these blue links, and triangulate it. So it looks kind of triangulated because there's lots of triangles in it, but let's just do, we could do a variable elimination scheme, that's always guaranteed to work, or we could just say, let's just take a look and check that there are no loops of like 4 or more which don't have chords in them. So in other words, every loop with 4 or more has a chord, and if it doesn't, we'll add one in. So that's their equivalent thing. So let's check. So I always get this wrong actually, but no matter how many times I look at this. Let's see where we can add something. So, so the red ones are triangulation things, okay, which are going to conclude. So let's say, why do we need? Okay, let's see. So. Why do we need this link B, D? Well, let's look at this. So B goes to E, goes to F, goes to G, goes to D, back to B. That's the loop of length 1, 2, 3, 4, 5. And there's no shortcut, there's no connection between these nodes. So don't get confused by this guy here. It looks like he's making it a shortcut, but he's not directly, he's another node, he's not part of that loop. There's no shortcut on this loop here. So we need to add one, say this one here. Sorry, I'm gonna just step back. The loop should have been this one, this one, this one, this one, down to C. Oh, that's terrible.
No, up to A.
BCDA?
Sorry, up to A. Yeah. And then we're in the situation as
Yeah.
yeah, because this C is not playing any role in that loop. It's just the A, B, E, F, G, D, A loop. That's a better one too.
Oh, I pick that. Why not?
I mean, maybe another way to visualize this is to.
Yeah. Yeah, okay, but why not pick A and G?
Hopefully, most of you can see it, but for those of you struggling with that, maybe you can kind of.
So you could say A to G, there could be just no shortcut.
Oh yeah, yeah.
You can say A,
Okay.
B,
So it's just.
D,
No.
A, B, sorry, A, B, E,
It doesn't put a lot
A,
of
B, E,
Right.
F, G, D, and C. So it looks like we have this loop here around the bottom. And C is just a kind of like a tent, lifting it up. But here's your loop, and there's no shortcut across this loop. But these things are quite tricky to spot, I have to say. So that explains why we might want to add a link between B and F, for example, and F and D, and similarly between B and D. Okay, so then this whole thing is surely, this ring around here is triangle, so that bit's okay. And C is clearly full of triangles, so that's okay. No problem there. And so the claim is, I mean, one would need to check this a little bit more carefully, but this graph now, the only more or less, the only triangulation links are the red ones now. So that's not bad. We would have to then write down all the cliques here. Now there are 4 cliques actually in this one, because if we look at it, C is, well, connected to the left side here. C, B, E, and F are all connected to each other. So there's a 4 clique there, and similarly there's a 4 clique on the right. This is a 4 clique there, and the rest are 3 cliques. So that's not bad, right? I mean, that means that at the cost now of 2 to the power 4 operations to represent these cliques, we can do inference on this graph. Just do message passing. Okay, so just to summarize this rather long story, what have we got? We've got, for discrete variables at least, we know then that carrying out this message passing operation is going to be exponential in the clique size, the largest clique size. Okay, so that's okay. So that's why we want to find ideally junction trees with small cliques, but it's not possible in general to do that. So I should say that is, so this algorithm, it always works, right? But it's an upper bound on the complexity. I mean, there may exist, even if you were able to find somehow the smallest clique, right? Maybe it's possible in some particular case. Maybe somebody even tells you, I know this is the smallest junction tree, clique with, junction tree with the smallest cliques. Even then, there may exist algebraic properties in your distribution which you're not exploiting here. This algorithm is very agnostic to any of that. It doesn't know anything about the fact that your Markov potentials or your belief network potentials have some particular algebraic property about them, which simplifies it even more. All we're using, it doesn't say anything about it. So we'll just take a potential, lump them all together, pile them, and that will always work. It's true, it will always work. But there might be something very special about the actual numerical form, algebraic form of that particular potential in your case, that this algorithm is not exploiting. And indeed, there exists remarkable instances in science where if you were to apply this junction tree algorithm, it would still appear that you would have to do an exponentially bad computation. However, if you think about it in a much, much more sophisticated way for that particular problem, there exist algebraic properties which render it polynomial time. These are very, very special objects and instances in science, and they are gold. If you find one, it's like you've got a pot of gold. You've got your name in lights. Right? If you can find such a non-trivial object, these are few and far between and very, very special. So a large part of computer science and mathematics is in identifying such objects. It's a big, big research field in itself. And they're fundamentally important, and the Nobel Prizes for physics were awarded for this as well. Okay, so in the 1930s, Onsager, when he did his stuff, came up with such a polynomial time algorithm. It's a little bit more complicated story, but effectively that's it. So even if you were to take this cleaning of this MRF object cleaning thing that you've been looking at in the assignment, that Markov network there is a lattice. It's not multi-connected. If you were to apply, try to find a junction tree for that, it's difficult. There is no junction tree which would not give rise to an exponentially large representation problem. In other words, the size of the cliques would always be a fraction of the actual number of nodes that you've got. So you're stuffed, basically. You cannot use a junction tree algorithm to do efficient inference, super efficient inference in the lattice case, Markov network case. However, remarkably enough, there exists with the Markov network and very special potentials if they're positive. There exist inference problems, such as finding the most likely state, which are actually polynomial in a number of variables. They're still quite difficult, they're badly polynomial. If you try to indeed run my binary MRF code with the actual polynomial algorithm, it's hopeless. It's very, 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 very slow. But it's formally speaking polynomial time rather than exponential. Okay. And there exists even an algorithm for finding the marginal of a single variable, which are also polynomial time for the same particular structure and same potentials. But that's a highly, highly non-trivial algorithm which was only discovered in the last 5 years or so. So this kind of interesting thing. So this is the point number 2. So point number 3, that you know, so this is going back to this ladder kind of situation. So you saw that ladder structure with the rungs in it. Right? You can see clearly that in that case, you know, there exists a linear time algorithm, even though it's horribly multiply connected. It's multiply connected. So there's another kind of you might say, yeah, but you know, this structure here, you know, you call that multiply connected, but actually, really, I can see in some sense there exists a kind of grouping of variables here, which sort of suggests it's really kind of singly connected on that grouping of variables. And this is called a hypertree. There exists actually, indeed, if I were to lump these variables together in some sense here, you know, this is a hypertree of width 2. How did they wish to define it? So, in other words, clearly within the junction tree framework, you know, this is all naive, you know, stuff. But actually, it's clear that there, you know, it's not the case that all multiply connected distributions are exponentially bad. Even in this case here, this is multiply connected, but it's linear time. It's trivially. There exist non-trivial situations like the field situations, which are multiply connected, for which there is non-trivially clear. It's not at all clear that you can do linear time or even closure. So yeah, I should say there's another terminology that that is used as well, called decomposable. If I haven't said that already today, that's another term. So the term a graph triangulated. If the graph is triangulated, it means the same thing for different communities as its chordal, which is the same thing as saying it's decomposable. So this is it's also called decimated. The physicists like this term. The mathematicians like this one, I think, mainly. This is more computer science, and this is more statistics. It's all the same thing. So you can see, you can imagine how important the concept this is in science. I cannot underemphasize the importance of this. I cannot overemphasize it either. You know, you get the idea. So similarly, you know, you can do, you can extend this to max as well. I'm just thinking, I mean, that's the end of this bit. So maybe I don't want to move on to anything else today in terms of, you know, new material, because I think it's enough for one day. But we've got another sort of 10 minutes, so maybe this is a good opportunity for you to ask me anything about the course up to this point. If there anything I can help you with in terms of clarification or hints for the assignment or hints for the exam. No? Is it all straightforward? Yeah.
Could you give a hint for question? What was it, 3 point? The one with the 3 computers. You know.
Oh gosh.
Yeah.
That's not a good
Yeah.
The computer one, yeah. What was that? 3.14. I tried to remember how I did this. Honestly, you know, most of these questions are, not all of them, but most of the questions I set myself. You know, so it's not that had to go and figure it out from somewhere else. So they are doable by me because I made the question. I think I think the thing to do is you have to try to understand the routes that are possible. So if you know, so the information you know is that you can get from 1 to 2 in 2 time steps.
Or
In
because it's plus. In the notation it means, yeah, you know, it could be a different route.
yeah, so you can. I think that means you can either say you can go from 1 to 2 in 1 time step and then stay at 2. Okay, so you could say a 1 and then go to 2. And similarly, you could go from 1 to 3 and then 3 to 2. So, and similarly for the other information, it says, well, you cannot do those things. So I think what you have to do is you have to write down then all of these possibilities and say, well, one way to do it is say, well, if you know this information, this actually is like evidence in some sense. You have a kind of, I don't know if this is the good thing to do, but you've got what is it, C1 to C1 to C1 3 C2 3. What else is there? 2 3 2 3. Oh, there's the other ones as well. The symmetric, the other parts are C2 1. C3-1 and C3-2. So I think that the question is saying that you want to try to figure out what are the probabilities of these being one and equal, or are they independent? And you've got some observations. Observations 1 and observation 2. Which is given by these things that you can. I have to think about it a little bit more, but basically each observation is a function then in terms of a belief network of some set or subset of these things. So let's imagine that that somebody says, well, you can get from 1 to 3 going via 2. Let's imagine that were, say, some of the evidence. It's not. Let's say that's evidence. That means that you have here a term. Let's say call this evidence for visible evidence number 1, which would say that probability V1 is equal to 1 given C12 and C23. Says that C so in other words, no, I'm not writing this down very well, but I'm trying to say that the fact that somebody tells you that you can get from 1 to 3 by going via 2, which means that you go from that C12 must be 1 and C23 must be 1. So you can write that down here. You could say this is evidence which tells me that the sum of these two, for example, must be 2. Yeah.
Just to clarification. First of all, are the communication links are symmetric or not?
Why do you say that?
So that C1 can send a message to 2 doesn't mean that 2 can send a message to 1. Okay. And secondly, you say at most. So it could be that you can also go with one step. With the other.
Yeah, you can go. You can stay in the same state. You can stay at the same computer.
No, I mean, when you say that
Yeah.
the CIJ parenthesis 2, okay, which means into at most two time steps you can go from one computer to the other. This includes the possibility that you can go from one computer to the other in one time step.
No.
No,
It means at least 2 times steps.
at least
More.
not.
What
It says at most.
Really?
Yeah, it says in the question you want to understand. Isn't it?
No, it says at
Yes.
two times.
Okay, it says so in the question.
So, I mean, it's some years since I said this question, I have to say. So I vaguely remember that one way to think about it is to think about it as a belief number and write down what evidence you have. This evidence, though, will be special in the sense that these distributions here they're hard distributions. They're either, they're kind of like they're not really the probability distributions, but they are enforcing that the parental variables are in particular states. Yeah.
It does say in the question that it can go in either 2 times step or 1. So what's the last few lines? In the second half.
Exactly 2 times.
So he says
At most, it's not
he wants 2 times this. So
And then it says no, but its message should not get by in different routes. It might go directly in 1 time step or indirectly into or both.
yes, that's true. Okay. Yeah, okay, that's true. It could go directly. And then, for example, stay in 3 for 1 time step, or it could stay in 1 time step and then go to 3. Yeah. So whatever the correct interpretation is.
That might be the question.
I mean, the tricky thing is, what I really want you to understand is that, you have a priori some prior probabilities on this connection activities, and you need to maybe, there's some care required in the interpretation of what the evidence is. But you've got evidence, which you can think of in terms of belief network. And then the idea is that given this evidence, you need to infer what are the a posteriori, the probabilities of each of these variables, the marginals of them being in state 1. It's doable. So in previous years, people have managed to do this question. Even myself, I managed to do this. Any more questions? Okay, so the other thing to say is if you do write things by hand, that's also fine, as long as you scan it, of course, and upload that scan. That's also fine.
Can we have a mixture?
Yes.
Different hand.
Yeah, different handwriting. Thrown it on scrapbook. Just paste it in. Yeah.